So let's look at page 407, number 28. So we have the functions y equals square root x and y equals x, but we're rotating this about the y-axis. So the things we want to be aware of is when you're rotating about the y-axis, that means you're going to be integrating dy, and it means you're going to need to solve the equations for x. All right. Now these equations are not solved for x, so we need to do that. So this one's going to be, it's pretty easy to do. This one's x equals y squared, and this one's x equals y. I mean, we don't even really need to do anything there. But we need to think of this not as the line y equals x, but the line x equals y, and this is the line x equals y squared. All right. Now we're rotating it around the y-axis. All right. By the way, it's easy enough to figure out that this is the point 0, 0, and this is the point 1, 1. Let's solve an equation, figure that out. So let me try and make this symmetrical-ish. I predict I'm going to make a mess of this drawing. I wanted you to see me struggle through the pain, so I didn't draw it ahead of time. Especially for those of you who have difficulty doing this, I want you to know that it pains me as well. Because we got to, like, this is a rotated thing. So some people can maybe visualize it from the cross sections here better. Like, think, you know, if I had cut this shape in half, then, you know, it looks like this, and like it has this trumpet-shaped indentation. So this, square rooty indentation going in. But the outside is conical, you see. So if I rotate it all the way around so that we can see the outside of it is conical all the way across. All right, it's nice and conical on the outside. But then it's got this concavity in the inside. So it's got this funnel shape that's cut out of a cone. So if I were just looking at this thing, if I flipped it over and set it on my desk, it would just be a cone, right? But then I would flip it over and go, oh, there's a hole in it, and that hole has this trumpety shape. Once again, with an exit point of diameter 0. So you can think about that if you want to. All right, could water flow out of it or not? Anyway, would it hold water with a hole in it whose diameter is 0? Let's see. I guess since an atom of water has a non-zero diameter, then yes, it would hold water. Not to mention the electrostatic repulsion, that even if it was larger than a molecule, the water probably wouldn't come out. Anyway, how do you do the volume of this? Well, it's the same idea. You think of an ith area element, you rotate it around, and it's going to make an ith volume element. I'm going to once again do like a cutaway view, half of it. All right, but what's really going on, of course, that goes all the way around. So now we have horizontal washers. Washers like that. So there's still washers. That's still a washer. But this time the height of the washer is delta y. So our v sub I is still equal to pi big R squared minus little r squared delta y. So yeah, I guess we could sort of just jump right to the integral. Maybe not. We can go ahead and put in that this big R is the outside function, so we'll call that g of x sub I squared, minus little r is the inside function, so that's f of x sub I squared delta y. And so what you're doing now, since it's horizontal, just like areas, you're doing the function on the right minus the function on the left. Although with these 3D shapes, it's probably helpful to always think of it as terms of outer minus inner, because we're going to move these things around and change their form a little bit. Outer minus inner is what you're doing, or you can just really think critically as what subtraction is going to get me a positive volume. And then you could look at the end and say, oh, if I got a negative volume, then I probably need to switch those two. All right, so that's that. And so that gives you, from this, you can get the integration formula again. So the integration, and you don't really have to derive the integration formula every time, but it's really important to see where it comes from. So our area is going to be the integral from a to b of g of y squared minus f of y squared dy, where now the a and the b, again, are y coordinates because we're doing dy. That always happens. If you're dy, the a and b are y coordinates. Doesn't matter what you're doing. This is going to be the right function minus the left function. Yeah. And then so let's put it in terms of the, once again, I forgot to show you the solution for the last problem. We'll do that. We'll do that after this. So here I'm going to have pi integral. It's 0 to 1. So in this one, it's a little misleading because both the x's and the y's go from 0 to 1. It's the y's. We're looking at the y's going from 0 to 1. So this was 0 and 2. We will go 0 to 2. All right, 0 to 1. So I'm going to put in my outer function, which is y, but I got to remember to square it, minus my inner function, which is y squared, but I got to square that. Right? Both functions get squared. So then I have, always simplify your integrand as much as possible before you start integrating y fourth dy. So then I have y cubed over 3 minus y fifth over 5, 0 to 1. So I have pi 1/3 minus 1/5 minus 0. 1/3 minus 1/5 is 2/15, so you got 2 pi over 15. Ba-ding! We found the volume of that thing. It's pretty cool, really. All right, let's go back and look at the solution to the prior problem because I forgot to show that. Here it is. Jink, it's 108 pi over 5. You can study that if you want. There isn't any like cool thing that happens. I don't have any helpful hints for evaluating this. Nothing useful happens. There's no symmetry. You have to deal with the 2 and the -1. It's a big mess. You just have to do all the fractions. There was nothing. The 24s cancel. One thing I do is like I have some things in terms of fifths. So I combine my fifths and my whole numbers separately. But, there's just really nothing helpful. And then I double check this on a calculator because I doubted myself. And I got, if I can find it up here, right there's my integral, 108 pi over 5. All right, so there you go. But you should always try to do these by hand because remember, they would absolutely expect you to do these by hand. All right, so here's a summary of what we've just been talking about. The compound solids, right? So we have this pair of formulas that we use for what I called simple solids, right here. Simple solids, no holes. Here's your equations. Just has one function, all right? Compound solids, they have a hole through the middle, all right? So they have two functions. This is x-axis rotation, this is y-axis rotation. So since you have y-axis, you have dy, your functions are solved for x, your limits are y coordinates, all right? When you do the x-axis rotation, you're solved for y because you have dx. Your limits are x coordinates. On the dx ones, you're going to do top minus bottom. On the dy ones, you're going to do right minus left, but just remember, make sure your area comes out positive and you can't go wrong. Okay, so just one last thing I'm going to do is look at some of the ones where these functions are a little bit less obvious, the second function, and then we can be done with this section. And I have the homework in the book is sort of a little scrambled for my taste, so I created some practice sets. So I think you're going to do, it's going to be called something like volumes number 1 and volumes number 2, which I think are attached here. And it's weird because I have to project into the future of what's going to happen. This whole thing involves so much more planning on my part. I never do this much planning ahead. Anyway, we'll look at some examples next.